adding the final shellcode. Welcome again. At this stage, you've earned more than just technical progress. You've built something far more valuable: control. You've observed the crash, identified the overwrite offset, redirected the program flow using a jump ESP instruction, and carefully carved out a safe memory space by eliminating bad characters. Now comes the moment we've been building toward: injecting and executing real shellcode. This lesson is about transition from redirection to execution. We're not just watching the program crash anymore, we're going to make it execute instructions of our choosing. That's what exploitation truly is. But before we inject anything into memory, let's step back and define what we're actually injecting, and why it matters. What is shellcode? Shellcode is a sequence of machine instructions injected into memory for execution. Despite its name, it doesn't have to open a shell. It can launch a calculator, open a reverse TCP connection, or run arbitrary commands. The term comes from its original purpose in the 1990s, spawning a shell on the target system. Today it's shorthand for any payload that performs an attacker-defined task when executed from within a process. In our case, we'll start with a simple payload, launching the Windows calculator. This proves that we can reliably execute injected code within the context of the VLC process. We'll use Metasploit's msfvenom utility to generate our shellcode. This tool enables us to create platform-specific payloads, apply encoding, and exclude any bad characters we previously identified. Before generating the payload, let's first inspect the required and optional parameters for the Windows/exec module. To do that, run the following. This command lists all configurable options for the Windows/exec payload. Among these, we can see that the cmd parameter is required. It specifies the command that will be executed when the payload runs. Knowing this is crucial, as it informs us that we must provide a command string when generating the payload. Now that we understand the required parameters, let's create the actual shellcode. Let's break this down. -p Windows/exec specifies the payload. It's designed to execute a system command. cmd equals calc.exe. This is the required parameter we discovered earlier. It tells the payload to launch the Windows calculator upon execution. -fc specifies the output format. In this case, we're using a C-style byte array, which can easily be embedded in an exploit script. -b x00, x0a, x0d, x2c. These are the bad characters we identified during our earlier testing phase. By excluding them, we ensure the payload doesn't break during injection. Press Enter to generate the shellcode. Once it's displayed, copy the output. We'll be integrating it into our exploit script in the next step. Now that we've generated our shellcode, it's time to embed it into the exploit. Start by opening your Python script for editing. Begin by removing the badchars array. We no longer need it, since we've already excluded the problematic bytes when generating the payload. Next, introduce a new variable called shellcode, and paste your generated payload there. Make sure the shellcode is enclosed within parentheses. If it's not properly wrapped, Python won't interpret it correctly as a byte array. Do bear in mind that if your shellcode is relatively large, you may need to adjust the total buffer length to maintain the correct offset to EIP. Now, update your final exploit construction line as follows. Once the script has been updated, save your changes and exit the editor. The final step is to generate a new subtitle file containing the updated payload. This file will be used to trigger the exploit with our functional shellcode. Switch over to your Windows XP target machine and relaunch Immunity Debugger. Start by removing the old .ssa subtitle file, then download the newly generated version. Now it's time to test everything in action. Before proceeding, set a breakpoint at the address used in your jump ESP instruction. This breakpoint ensures that execution will pause just before control is redirected to the payload. Once the breakpoint is in place, open the subtitle file in VLC. At this point, Immunity Debugger should pause execution at the jump instruction. Press Shift F7 to step into it. Next, right-click the EIP value, hover over Follow in Dump, and click Selection. This step allows us to follow execution directly into the region of memory containing our shellcode. To confirm the shellcode is accurate, I'll display the contents of our exploit script using the cat command. We can now visually compare the shellcode bytes in memory with the script output. A quick inspection shows that the initial byte sequence matches exactly XB8, X33, XF8, X9E, XA4, and so on. As you can see, the memory content matches perfectly. This confirms we've landed exactly at the start of our shellcode. Let's continue. We've now reached the junk section, clearly marked by the presence of hexadecimal CC values, as reflected both in the EIP value and in the memory view just after the shellcode. These are intentional padding bytes we placed to help identify boundaries. Next, right-click on ESP and follow it in dump. Good. The memory pointed to by ESP gives us a clear view of the remaining space available. It's more than enough to safely accommodate our shellcode. Back in the exploit script, I'll add 32 nops to create a sled. This should provide sufficient buffer space before the shellcode begins, giving the CPU a safe landing zone in case ESP doesn't land exactly on the first byte. Make sure to define the NOP sled immediately after the EIP variable. Then, update your exploit construction line to follow the correct layout. At this point, we've placed the sled where it belongs, right after the jump. The shellcode sits directly after it, exactly where execution is meant to flow. With this structure in place, the buffer layout is now finalized and ready for reliable reuse. Save, and close the script. Switch over to your Windows XP target machine and relaunch Immunity Debugger. Start by removing the old .ssa subtitle file, then download the newly generated version. Next, launch VLC Media Player and wait for it to load fully. Before proceeding, set a breakpoint at the address used in your jump ESP instruction. This ensures that execution will pause just before control is redirected to the payload. Once the breakpoint is set, open the subtitle file in VLC. At this point, Immunity Debugger should halt execution precisely at the jump instruction. Press Shift F7 to step through and confirm that it lands on the NOP sled. If everything has been correctly aligned, you should land directly on the NOP sled. From here, you can continue stepping through the instructions to observe the flow into your shellcode, or simply press F9 to resume normal execution. If the exploit is functioning as intended, the calculator will launch confirming that your payload has successfully executed within VLC's process space. At this point, you no longer need Immunity Debugger. To demonstrate a seamless end-to-end exploit, simply double-click the .ssa file. The calculator will execute automatically. No breakpoints, no debugging, just payload execution. Congratulations! You've now completed a full-stack buffer overflow exploit, progressing from raw input file to full shellcode execution inside a live process. This marks a critical milestone in your development as a vulnerability researcher. Verifying exploit stability. If the calculator launches inconsistently or not at all, don't panic. This usually points to issues with alignment, memory layout, or unintended corruption. Here's what to check. Ensure the shellcode appears intact in memory, without truncation or distortion. Confirm that no bad characters were introduced during copy-paste or formatting. Verify that ESP lands precisely at the start of the NOP sled, allowing a clean slide into the payload. Double-check that your payload doesn't accidentally overwrite critical stack structures, which could lead to instability or premature crashes. Stability comes down to precision. Even minor shifts in the buffer layout can break execution, so test thoroughly and adjust as needed. Let's take a moment to appreciate what we've done. We began with a malformed subtitle file, a simple sequence of characters in a text file. And now, that same file has overwritten the instruction pointer, redirected execution into controlled memory, slid safely through a NOP sled, and successfully executed machine code inside a live process. This is exploitation in its purest form, turning a programming flaw into a point of control. Now that you've successfully executed custom shellcode within VLC, it's time to deepen your understanding and test the flexibility of your exploit. Try the following exercises. 1. Replace the calculator shellcode with a different payload such as the following, and see if the new payload works out of the box. 2. Test shellcode with and without a NOP sled. How sensitive is execution alignment? What happens if ESP lands a few bytes off target? 3. Use msfvenom to generate a reverse shell payload and connect it to a netcat listener. How does the environment respond to real-world payloads? These exercises will help you reinforce control, adapt payload behavior, and simulate post-exploitation scenarios in a realistic setting. In the next and final lesson, we'll go one step further and port this exploit into a Metasploit module, making it easily reusable and shareable within offensive security frameworks. You've nearly completed the full cycle of exploit development.